everybody. Welcome back to Mathematical Statistics. We are finding UMVUEs, uniformly minimum variance unbiased estimators. And we found some examples last time, and I wanted to start off with a few more. So our main tool for finding UMVUEs is the Lehmann-Scheffé theorem. So just a quick recap there in my usual sloppy theorem style where I just sort of write things out with bullets. But suppose you have an x1 through xn IID from a distribution that depends on an unknown parameter or a vector of parameters theta. And suppose that we want an, but I'm going to say the, because this is actually a unique thing, which I've yet to show, an UMVUE for theta or a function of theta, tau of theta, which could be theta itself. There are two steps to take. Step one is going to be to find a complete and sufficient statistic S. Now, if the parameter is not in the indicator, for you, this is almost always going to be to look at the exponential family factorizations. They may fail, but that's where I'd look first if the parameter is not in the indicator. Otherwise, it's a little harder. And the second step is to find a function of S that is unbiased for, or let me say, whose expected value is the target, the tau of theta. So let's look at a new example. And I think this one you're going to find to be a little interesting for reasons. So suppose I have x1 through xn, a random sample from the Poisson distribution with parameter lambda. Let's find the UMVUE for tau of lambda defined to be e to the negative lambda. To be careful there, my lambda is looking a little bit like my x's. Okay, so step one is to find a complete and sufficient statistic. Since it's written on the slide right here, I won't rewrite that. And because the parameter is not in the indicator here, the first thing I'm going to try is the exponential family factorization. So let's try to write down the joint PDF. Because we have IID random variables, this is a product as I goes from 1 to n, e to the minus lambda, lambda to the xi over xi factorial times an indicator that says that xi is between 0 and 1. When we multiply this out, we'll get e to the minus n lambda, lambda to the sum of the xi. That sum goes from 1 to n. Product as I goes from 1 to n of the xi factorial, and that factorial has to stay in there. This is not the product all factorialed. And then a product of indicators. So for the exponential family factorization, we're looking for a part that is pure parameter, like an a of theta, a part that is pure data, like a b of x, and then an e of a pure parameter part, c of theta, times a pure data part, d of x. And if we can do that, then the statistic given by d of x is complete and sufficient for the model. This appears to be some pure parameter stuff, so let's start there. This is e to the minus n lambda. This is pure data and pure data, so, let's do it. I could write this as one product, but I don't think I will. That's a weird term to have an indicator divided by a factorial, but you can do it. It doesn't matter. It's not the term we care about, but this would be my a of lambda, and this would be my b of x. Now, the remaining part I'm going to do on the side before I write it here. We have lambda to the sum of the x's, and we can write this as e of the log of lambda to the sum of the x's. And the exponents on logs can come down in front, so we get the sum of the x's times the log of lambda. And not that we have to get right into this form. Oh, this should be a lambda. But I am going to reorder these things in this product just so it looks super nice. We get e to the log of lambda, and then the sum of the xi, and this is going to be our c of lambda our d of x. Okay, so we're going to pull out our d of x, and we can say by one parameter exponential family, the statistic S, which is defined to be d of the capital X's, which in our case is the sum as I goes from 1 to n of the capital Xi, is complete and sufficient for this model. So we're done with step 1. Step 2, remember, we're trying to find the UMVUE for tau of lambda, defined to be e to the minus lambda. Usually the first thing I do here is look at the expectation of the complete and sufficient statistic and see if I can adjust it. The mean of the distribution is lambda, and we know we can get an unbiased estimator out of the sample mean, x bar. And so you might try something like e to the minus x bar, but we've done this before, and we did not get anything good. This example you've seen before in the Rao-Blackwell section of the course, which was a couple of videos ago, 2 to 3 videos ago. The Rao-Blackwell theorem had nothing to do with complete statistics, and it didn't appear to have anything to do with an UMVUE. But it took an unbiased estimator for something and conditioned on a sufficient statistic to get another unbiased estimator for the thing that is a function of the sufficient statistic. And I don't really care to cite that the Rao-Blackwell theorem lowered the variance. What we want is an unbiased estimator that it's a function of this. It's sufficient, and it also happens to be complete. And in this example, we started with an unbiased estimator, which was the indicator that x1 was 0, because the expected value of an indicator is the probability of the thing being indicated, and this function is the probability that one of them is 0. But this is not a function of all of the data, and now, in the context of the UMVUE, it is not a function of this sum. But if we Rao-Blackwellize this estimator by computing its expected value given this sufficient statistic, we will get something that is still unbiased for this function and is a function of S. That's what the Rao-Blackwell theorem did for us. But it turns out if S happens to also be complete, which is not something we talked about back then, we've got a function of the complete and sufficient statistic whose expected value is our target. We have the UMVUE via the Rao-Blackwellization. So I'm not going to drag you through that whole thing again. You can go check it out in a past video, again, maybe 2 or 3 ago. I don't think it was the last video, but maybe the one right before that. And yeah, we found that an unbiased estimator, like I'll call this tau lambda 1 hat, but we found an unbiased estimator, and it was kind of strange. I mean, it was not guessable. It was n minus 1 over n raised to the s, or if we want to see the x's in there, n minus 1 over n raised to the sum of the x's. And we did this, again, I just want to write this for the record, by the Rao-Blackwell theorem in a previous example. This is a function of the complete and sufficient statistic whose expected value is the thing we're trying to estimate. So this is the UMVUE for tau of lambda defined as e to the minus lambda. So I thought that was a cute example because we can use the Rao-Blackwell theorem maybe to find an UMVUE, even though we weren't talking about completeness back then, or even minimum variance. We were talking about lowering the variance. But it works because it gives us a function that's still unbiased and is a function of S. Okay, let's do one more straight UMVUE example. So suppose I have x1 through xn IID from a distribution with the following PDF. So I'm not going to name this one. 2 theta 1 minus x over 2x minus x squared to the 1 minus theta and an indicator saying that x is between 0 and 1. Let's find the UMVUE for just theta itself, or tau of theta equals theta. Step 1 is going to be to find a complete and sufficient statistic. Because the parameter is not in the indicator, there's a good chance that we'll get an exponential family factorization here where we can pull out the d of x. So let's try it. So step 1, I'm going to write down the joint PDF. Because these are IID, we get this from the product of, let's see, 2 theta 1 minus xi over 2xi minus xi squared to the 1 minus theta, and then an indicator putting xi between 0 and 1. If we multiply this out, I get 2 to the n, theta to the n. I get a product as I goes from 1 to n of 1 minus xi. I get a product in the denominator of terms like this. But since we're going for that separation of the x's and the parameter, I'm going to go ahead and pull that exponent out of the product and write this as the product as I goes from 1 to n of 2xi minus xi squared raised to the 1 minus theta. So yeah, it's okay if you had left that in here, but eventually you're going to have to pull it out to get the separation we want. And then finally, a product as I goes from 1 to n of the indicators. So we're looking for an a of theta, a b of x, and an e of a c of theta, d of x. This looks like pure theta stuff. You could put that 2 to the n anywhere. This looks like pure x stuff, and so does this. And then here is where the x's and the thetas are kind of tangled up. So we're going to do our e and log trick. Maybe you'll find, I don't know, just do it. Maybe you don't want to follow my steps. I was going to say that maybe you'll find this easier to first put that denominator up and not have any denominator. So this could be like 2 to the n, theta to the n. Let's get it in that order. The product as, I'll put these products together. The product as I goes from 1 to n of 1 minus xi times the indicator that says that xi is between 0 and 1. And then I'll write this as the product as I goes from 1 to n, 2xi minus xi squared raised to the theta minus 1, because I put it, from the denominator up on the numerator. So I'm going to take e of the log of this and bring this down. And I will have a log of a product left, which is a fine answer for a complete and sufficient statistic. But as you know, we're going to need to work with it in step 2. So probably the log of the product should be written as the sum of the logs. And if you don't do that now, you'll do it once you hit step 2. So let me do a little copy and paste here. Okay. This is going to be e, and then theta minus 1 times the sum as I goes from 1 to n of the log 2xi minus xi squared. So this is my a of theta, or you could put that 2 to the n with one of the other functions. This is my b of x. This is my c of theta. And this is my d of x. Okay, so by one parameter exponential family, the statistic S that is defined to be d with the capital X's plugged in, which in this case is the sum as I goes from 1 to n of the log of 2xi minus xi squared. This is complete and sufficient for this model. So we're done with step 1 of the Lehmann-Scheffé theorem. Remember, we're trying to find an UMVUE for theta itself. Okay, so step 2. Step 2 is to find a function of s whose expected value is theta, or find an unbiased estimator of theta find a function of s that is an unbiased estimator for theta. So if you didn't write this as a sum of logs and had a log of products, at this point, you're probably going to move that outside because we need to look at the distribution of this thing, and sums are always easier. You could, well, what I usually do, as you know, is I take the expected value of the statistic. And if we pull that sum through, we've got this. Now, I think you can compute this expectation using an integral by putting this function in front of the given PDF. I think there'll be a decent u substitution in there for you to do that integral, but I try to avoid integrating whenever I can. And you know what I would do in a situation like this. You don't have to do it, but I would look for the distribution of this. It may not come out nice, but I'm hopeful. So again, you can go for this expectation by putting this function in front of the original PDF and integrating. And I think that one is doable, but I'm going to do it differently. I'm going to say I've got y equals g of x equals the log of 2x minus x squared. What is x? There is no x in this problem. There's x1 through xn, but I'm about to do that g inverse stuff that we did at the beginning of class. And I'm just doing it on one of the x's. So if you want to call this x x1 throughout, you can. But this is a y equals g of x equals the log of 2x minus x squared. And if we solve for x, we'll take e of both sides. So we'll get this. And if I move everything to the left, I'll get x squared minus 2x plus e to the y equals 0, a quadratic. Let's try the quadratic formula. X is negative b plus or minus the square root of b squared minus 4ac over 2a. In this problem, a is the lead coefficient, which is 1, b is the negative 2, and c is e to the y. So I will get positive 2 plus or minus the square root of b squared, which is 4, minus 4ac over 2a. And I can simplify this a little bit. I can pull that 4 out under the square root and take the square root. It'll be 2. And then I'll get to cancel a lot of 2's. And this will be 1 plus or minus the square root of 1 minus e to the y. Two solutions. So what do we use? Remember, in this problem, x was between 0 and 1. So I don't want to use this positive solution because that'll be something greater than 1. Yes, you might worry about whether you're taking a negative under the square root, but there's no way that the square root of something is going to be negative. So taking this solution with the plus here is going to be out of the range for the random variable. And so I am going to take my x, or g inverse y, to be 1 minus the square root of 1 minus e to the y. Okay, so remember our fy of y, and you certainly can put a semicolon theta in there, but back when we did this g inverse stuff, we didn't have that notation. So I don't know what you want to do, but I'll just go with our old notation, absolute value, d dy, g inverse of y. Okay, we have 2 theta 1 minus x. So that's going to be 1 minus the square root of 1 minus e to the y. I didn't work this one out beforehand. I hope this works out well. In the denominator, we had 2 times x. So that's going to be 2 times this thing. We'll get 2 minus the square root of 1 minus e to the y minus x squared. So minus 1 minus the square root of 1 minus e to the y squared. And all of that was raised to the 1 minus theta. And we had an indicator saying that x was between 0 and 1. And our x is now 1 minus the square root of 1 minus e to the y. And don't forget this. So I'm going to take the derivative of this. Whew, this is messy. I'll get 0 minus, so that square root is like a 1/2 power. I'll get 1/2, 1 minus e to the y to the negative 1/2 times the derivative of the inside, which is negative e to the y, all in the absolute value. Let's see if we can simplify this. Okay, here I'm going to, let me get this, sorry, it's color going. I am going to subtract these guys, and I am going to square this out. So that's what I'm doing next. So in this numerator, I get 2 theta square root of 1 minus e to the y. I'm just trying to decide if I want to pull this in yet. Let's square out that thing in the bottom. I have 2 minus the square root of 1 minus e to the y minus 1 minus 2 square root of 1 minus e to the y plus 1 minus e to the y. And then that entire denominator is raised to the 1 minus theta. I'm going to skip the indicator for the moment and simplify this. I have a negative and negative, which wouldn't have mattered anyway because the absolute value. And we have, we have 1/2 e to the y over the square root of 1 minus e to the y. So this all goes like up here. Let's take care of the indicator. We want this expression to be between 0 and 1. So 1 minus the square root of 1 minus e to the y, we want that between 0 and 1. And so I would subtract the 1 all the way across. Then I might take care of the negative and flip everything. Then I would square everything. And just in the interest of time, I can tell that this is going to be, we're going to end up with y between minus infinity and 0. Which leaves me a little worried about recognizing this distribution and being able to work with it. And then again, it doesn't. Maybe I should have chosen my y a little bit differently. But I'm going to come back up here and multiply by the indicator that says that y is between negative infinity and 0. Okay, let's see. This 2 and this 1/2, because this is in the numerator, even though it doesn't look like it, will cancel. This whole square root up here and this one will cancel. This should have been multiplied by 2. I was plugging this in to something that was 2x. So I am missing a 2 right here. Sorry about that. And with this negative and this negative, I have this and the positive of this. So that's actually going to cancel this term and this term. Kind of nice. What is left? I have theta, that's from here, e to the y, just from here. This term's gone and this term's gone. I have 2 minus 1. I am making a mess out of this. So I have 1. And then this negative on here gives me negative 1 minus e to the y. And the entire denominator is raised to the 1 minus theta. And my indicator says that y is between 0 and infinity. So let's cancel this stuff. I have theta e to the y over positive e to the y to the 1 minus theta, an indicator. Just starting to look exponential. This denominator is e to the y minus theta y, and this e to the y is going to cancel with this one. And if I move the rest of this into the numerator, I get theta e to the positive theta y. And so thankful that that simplified because I didn't work it out ahead of time. This is the PDF for y, which was defined to be the log of 2x minus x squared. And it looks exponential, but we're missing a negative up here, and this is the wrong space. So you could leave it and work with this new random variable, but I would just go back. I wouldn't go back literally and say, instead, define y to be the negative of the log of 2x minus x squared. You go back through what we just did and trace that through, then it's easy to see that y has an exponential distribution with rate theta, but not until you put that negative on. Okay, what were we trying to do in step 2? We were trying to find the expected value of s. This was the sum as I goes from 1 to n of the expected value of the log of 2xi minus xi squared. You could leave that sum inside. We almost have an exponential. We need to adjust it. And the sum of exponentials would be gamma, and you could work with that. But I'm going to leave the sum outside. But I would like to have a negative in here. So I'm going to say this is the negative of the sum as I goes from 1 to n of the expected value of the negative of the log of 2xi minus xi squared. This is our new definition of yi, and it is exponential with rate theta. And the mean for an exponential, let me write this again, is 1 over theta. So this is the negative of the sum of a bunch of 1 over thetas, which gives us n over theta. So much regret right now that I didn't work this out ahead of time. We are looking for theta itself. And so this is not easily adjustable because the theta is in the denominator. But let's finish it. I would hate to stop it here. So I could multiply my s by negative 1 over n, and I would get 1 over theta, but that's not what we want. So I am going to try the expected value of negative 1 over s. Negative 1 over s is the negative of 1 over the sum of these logs. I can bring that negative down in here. Then I have 1 over the sum of the yi's defined with the negative. The yi's are exponential with rate theta. This is a sum from 1 to n. So this has down here a gamma distribution with parameters n and theta, assuming you're using the parameterization of the gamma distribution we're using in here. Okay, so let's call this, we have a name for it, kind of. This is negative s. So maybe you want to call it something else, but negative s has a gamma distribution with parameters n and theta. The negatives are a little weird here. Maybe I should rewrite this. I should let w be the negative of s, which has this gamma distribution. And so now we're looking at the expected value of 1 over w. This is going to be the integral 0 to infinity 1 over w times that gamma PDF, 1 over gamma of n, theta to the n, w to the n minus 1, e to the minus theta w dw. I'm going to bring that w in there and adjust this and integrate without integrating. Or maybe you remember this result because we've done it a few times. But I'm going to kind of skip ahead just a little bit. I'm going to write this as w to the n minus 2, e to the minus theta w dw. And now I need this to be theta to the n minus 1, 1 over gamma n minus 1. So I need a gamma n minus 1 here, and the original gamma n down here, and one of these thetas out here, so that these will total up to theta to the n. Okay, so now I do have the integral of the PDF of the gamma distribution with parameters n minus 1 and theta, and we know this is 1. And this becomes gamma n minus 1 over n minus 1, gamma n minus 1 theta. So 1 over n minus 1 theta. Whew. Let's finish this off. If I just want a theta, I need to put n minus 1 in front here. So we're done. The UMVUE for theta is n minus 1 over w, which is n minus 1 over the negative of s, which is n minus 1 over the negative sum as I goes from 1 to n of the log of 2xi minus xi squared. That is the UMVUE. It is unbiased for theta, and it is a function of the complete and sufficient statistic, which is this s in here. That was way longer than I intended, but that was kind of fun. And yet another chance for us to pull all of our skills together from the entire semester. Next up, we have the concept of minimal sufficient statistics. So a sufficient statistic, there are many sufficient statistics for each model, but we are generally trying to reduce stuff down to the minimum of what we need to estimate the parameter. There are many sufficient statistics for a model, but we're generally going for the smallest dimension sufficient statistic, which is like the biggest reduction from the data to a lower dimensional thing that we can work with to estimate the unknown parameter. Some people think that the definition of a minimal sufficient statistic is a sufficient statistic of lower dimension. That's not really correct, although I guess we can make an argument for some people define it that way, but it's really a minority. That I'm just going to say that's incorrect. Um, but it's not a bad way to think about things. If you're looking for a minimal sufficient statistic and you find a sufficient statistic using the factorization criterion, you'll remember we had an example with the uniform zero theta distribution where we had a joint PDF and we rewrote it and we rewrote it again and we kept getting lower dimensional sufficient statistics. A minimal sufficient statistic is not really defined in terms of its dimension, but it is going to have low dimension. So if you're looking for one, that's a good place to start. But how do we actually define it? So imagine you have a model, you've got a theta, you've got your x's, a statistic s, which is going to be some function of the data, capital X, is a minimal sufficient statistic for the model, for estimating P for a Bernoulli distribution, or estimating a function of P for the Bernoulli distribution, or, we've been using this for the model for a while, if two things hold. Number one, S needs to be sufficient. And number two, S needs to be a function of any other sufficient statistic for the model. Let's talk about that dimensionality argument again. If we have x1 through xn, IID, uniform 0 theta, then the joint PDF is 1 over theta to the n times a product as I goes from 1 to n of the indicator that says that each xi is between 0 and theta. We rewrote this a couple of ways. One is the product that says that the min and the max are both between 0 and theta. And then finally, one with just the maximum. We put the minimum between 0 and the maximum. So that depends only on the x's, and the maximum between 0 and theta. And so by the factorization criterion, we have the pure x stuff, which is the h of x, and the rest of it is the g of s of x. And we go in and we find how the data is represented and it's represented through a maximum, this should have a parentheses on that. And so we know that the statistic that is the maximum is sufficient by the factorization criterion. But we also said that you can stop the simplification in any of the lines above. So this is one sufficient statistic. Another one would be to have both the max and the min. That is more than sufficient, right? Another one would be to have all of the data. If anyone ever asks you, does a sufficient statistic always exist? You say yes, because you can always take the n-dimensional statistic consisting of all the data. Minimal sufficiency is not really a dimension thing. As some people say, it's the sufficient statistic of lowest dimension. And then you would say, well, this has dimension 1. I can't go lower than that. So this must be minimal sufficient. That's not quite right. The thing I circled happens to be a minimal sufficient statistic, and we will show that either today or on Wednesday. But it should be, lowest dimension should be what you're thinking about if you're sort of aiming for something minimal sufficient. And then we can use the definition of minimal sufficiency to see whether or not the thing I circled is actually minimally sufficient. Let me give you one more example where using the dimensionality argument will give you trouble. So this is an example of don't use lowest dimension as your definition for a minimal sufficient statistic. I'm just going to show you an example where this is going to cause us problems. I'm going to make it nice and simple and have only a sample of size 1. So suppose I have x1 normally distributed with mean 0 and variance sigma squared. If you write out the joint PDF, which is just the single PDF, you get 1 over the square root of 2 pi sigma squared e to the minus 1 over 2 sigma squared x1 squared. This is already in the exponential family factorization. I don't appear to have a b of x, but that's okay. Your b of x could be identically 1, or you can pull the 2 pi stuff into the b of x. But this looks like an a of sigma squared, and then e of c of sigma squared, and d of x. So by one parameter exponential family, the statistic s, defined to be our data point squared, is complete and sufficient. I am going to call this S1 because we also know that the full data set, which consists of one data point, S2 being X1 alone, is sufficient for the same reason I always say you can take all of the data and because there's just one data point. So note a couple of things. S1 is a function of S2, but not the other way around. So even though this is a sufficient statistic of lowest dimension, it's not a minimal sufficient statistic. You can't get it back from knowing the value of x1 squared. If you know the value of x1 squared is 3, then x1 itself might be the square root of 3 or the negative square root of 3. So although we have yet to see how to show something is minimally sufficient, I claim that S1 as x1 squared is minimally sufficient. And I have a theorem for you next, right after this example, where we can get this result. But S2 is not minimally sufficient, even though it is sufficient. So I think I said that in a kind of convoluted way, but it's a one-dimensional sufficient statistic, and yet it's not minimal sufficient. And so if you're a person that says that minimal sufficient statistics are statistics that are sufficient and of lowest dimension, and then you say one dimension has to be as low as you can go, you're actually going to get it wrong for some problems. Okay, I do need to show that this is minimally sufficient. And to do this, I'm going to use a very famous theorem due to Bahadur. Bahadur's theorem. This is awesome. This is so useful. Showing minimal sufficiency is in general hard to do, but this goes a little something like this. If S, and start with a model and a theta, is complete and sufficient, then S is minimally sufficient or minimal sufficient. That is awesome because we have seen a lot of complete and sufficient statistics, and we can use our exponential family factorization to get a lot of them. Remember, all these statistics could be vector valued, like sum of the x's and the sum of the x's squared. If you're estimating two parameters, like a normal mu sigma squared, this is an amazingly easy to apply result for minimal sufficiency. So in the remaining time, I am going to prove this. Actually, I think I have even more time. I am going to do a proof assuming the existence of a minimal sufficient statistic. Okay, we do not need a minimal sufficient statistic to exist for Bahadur's theorem to hold. And I am going to put a proof without this assumption up on the Canvas page. But that proof is way more tedious. And so I just want to do a simpler proof because we don't have a lot of time left. And I really don't want to drag this into a second day. So this is just to simplify the proof. I am also working on a document for you that talks about sufficiency, completeness, and minimal sufficiency, and just everything. Does this always exist? Does this exist if this exists? Does this imply this? And I'm almost done with that. So I should have that done by Wednesday as well. Let's prove it. I am going to assume the existence of a minimal sufficient statistic. So I'm going to let S be a complete and sufficient statistic. I am going to let capital M be a minimal sufficient statistic because I'm assuming one exists. So let's grab one. And I am going to consider the expression. Actually, let me tell you what I'm going to show. I will show that S is a function of M. Now, M is minimal sufficient, so M is a function of every other sufficient statistic, but S is a function of M, which is a function of every other possible sufficient statistic, which means S is minimal sufficient. So then S is a function of any other sufficient statistic. So it is minimally sufficient, which is what I'm trying to show. Again, we're trying to show that a complete and sufficient statistic is minimally sufficient if we assume the existence of a minimally sufficient statistic and show that S is a function of that minimally sufficient statistic. That minimally sufficient statistic is a function of every other sufficient statistic. So we've got that S is a function of every other sufficient statistic and is therefore minimally sufficient, and we're done. Okay, so to show this, I'd like you to consider the expression S minus the expected value of S given M. This is a random variable, right? Because S is capital over here, And this expectation is going to be a function of the capital M. I don't have an M equals little m there. So this is a random quantity. And over here, as I just said, this is a function of M, but M is minimally sufficient. So this is therefore a function of S, since M is minimally sufficient. This is a function of S. So this entire thing is a function of S if you look at it in the right way. At first glance, it looks like it's a function of S and M, but M is a function of S. I'm going to take its expectation. The expected value of S minus the expected value of S given M is the expected value of S minus the expected value of the expected value of S given M. And we've got our law of the iterated expectation there. That second expectation is just the expected value of S. So we get 0. But inside here, we've got a function of S, like a g of S, and the expectation is 0. And because S is complete, we know that g of S must be 0 with probability 1. So S complete implies that g of S is 0 with probability 1 as a result of the expected value of g of S being 0. So this is the expected value of g of S is 0. So g of S has to be 0 with probability 1. What is g of S? It's S minus the expected value of S given M is 0 with probability 1. This means that S is the expected value of S given M with probability 1. So S is written as this expectation, but as we've talked about already, this is a function of M. And that's what we were trying to show. So S is a function of M, and M is a function of any other given sufficient statistic. So S is sufficient and a function of every other given sufficient statistic. So S is a function of any other sufficient statistic. Now, S was given to be complete and sufficient, so we do have the sufficiency. Because for minimal sufficiency, there are two things to check. One is that it's sufficient, which was given in the setup here. It was sufficient and complete. And the other is that it is a function of all other sufficient statistics. It's not terminology that's used a lot, but if you had S as a function of every other sufficient statistic, but not sufficient itself, it's known as a necessary statistic. It's rarely used. Don't worry about that. That's just a fun fact. Okay, so as an example, and this is going to be a real quick example. If we have x1 through xn, IID, uniform 0 theta, we do not have an exponential family factorization here. So if you want to find a minimally sufficient statistic, you could do that sort of directly. I have another theorem coming up next that's a little more direct for this, or you can find something that's complete and sufficient. Now, in this case, because it was not exponential family, we used the factorization criterion to get something that was sufficient. And then we showed by definition of completeness, it was complete. We had S as the maximum is both complete and sufficient. We've shown it in the past more than once. And so by Bahadur's theorem, this maximum is minimal sufficient or minimally sufficient, usually minimal sufficient. I don't think I've convinced you yet why you care about minimal sufficiency, but right now we have a definition and we have sort of a way to find some. Okay. So I have a bit of time, but not, yeah. Let's at least start the next theorem for the purpose of forward momentum. Another way to find a minimally sufficient statistic, a minimal sufficient statistic, or to verify that something is minimal sufficient is given by this very useful theorem. Given a setup, an x1 through xn, and a theta, and a PDF, and a joint PDF, it goes like this. A statistic, I'll call it T, could call it S, is minimally sufficient, minimal sufficient. I don't know why I keep saying minimally. The term is minimal sufficient for the model if this following if and only if thing holds. So if you look at the joint PDF evaluated at some little x1 through little xn divided by the joint PDF evaluated at a little y1 through little yn. If this is theta free, doesn't depend on theta, if and only if this function t of the vector of x's is equal to t of the vector of y's. This is not an if and only if. So this is a sufficient condition for minimal sufficiency. It's not necessary and sufficient. This, of course, is an if and only if. Let's just do an example, and I'll rather than start the proof and finish it next time. So we'll prove this next time. And I just want to do something super easy. We picked a lot of hard examples. I picked a lot of hard examples today. So just like Bernoulli random variables, we already know how to find a minimal sufficient statistic here because it is an exponential family. So we know how to pop out a complete and sufficient statistic. And by Bahadur's theorem, that is minimally sufficient. But let's try to use this theorem. So the joint PDF is the product, right? IID, this I goes from 1 to n of p to the xi, 1 minus p to the 1 minus xi, and an indicator, right? When you're using theorems that say this is parameter free, the indicators are important. So an indicator that says that each xi is between 0 and 1, and let's condense this into p to the sum of the x's, 1 minus p to the n minus the sum of the x's, and a product as I goes from 1 to n of the indicators. So let's try to form this ratio, f of the vector x and p over f of the vector y and p. We're going to get, it is easy to see that if the sum of the x's is equal to the sum of the y's, that we're going to get a lot of cancellation, and this is going to be parameter free. So that's one direction of that if and only if. To really see the other direction, I would spend some time to simplify this a little bit more. You can cancel this part of, this exponent. So we've got 1 minus p to the n in the numerator and the denominator. In the numerator, I've got p divided by 1 minus p to the sum of the x's. So got the same thing in the denominator with the y's. And these indicators don't cancel because the x's are not necessarily equal to the y's. So it's just sitting there in both the numerator and the denominator. So maybe you want to rewrite this as p times 1 minus p raised to the sum of the x's minus the sum of the y's. You know what? I'm going to do it. And then the indicator stuff. So this needs to be parameter free. The parameter is p. And so in this form, you can see that this is parameter free if that disappears if and only if the sum of the x's is equal to the sum of the y. So in this problem, I didn't start out with a statistic t of x that I was trying to show was minimally sufficient. I just sort of wrote out that so-called likelihood ratio, and something popped out. This is t of x. It's the sum of the x's. And so now if you go back to the beginning and look at the theorem and use this t, you can see that the likelihood ratio is parameter free if and only if t of x is equal to t of y, assuming you defined your t of x like this. So the sum, as I goes from 1 to n of the xi, is minimal sufficient for the Bernoulli model. Again, we already knew this because we knew it was complete and sufficient, and we have Bahadur's theorem. But I just wanted to show you how to apply this theorem to maybe find something that's minimally sufficient if you couldn't find a complete and sufficient statistic. Or we'll see next time that we could propose something is minimally sufficient and use this theorem to verify. And we're going to prove it. And then we're going to talk about ancillary statistics and Bassou's theorem. And we're getting close to our final topic this semester, which is going to be to go back to hypothesis testing, but to do it all crazy general like with things. So please come back. Hope to see you next time on mathematical statistics.